first challenge will be on the first machine learning method that we saw, which was k-means clustering, right? So the idea here is that you have this very simple algorithm in theory, right? So you have multiple points in space. You initialize some of the points in the space to be your cluster representative. Then you assign the points to the cluster. Then once you have assigned the points to the cluster, then you reinitialize the cluster representatives, and you keep repeating this until you converge to some solution, some stable solution in which you have identified some of the some meaningful way of clustering your data, which reveals some underlying pattern in the data, right? So this is a an unsupervised learning approach. And so since it's unsupervised, then you're sort of hoping to find some pattern in the data which you were not able to identify originally. Okay, so there is no label Y, there are just features, and you're trying to group the features. Okay, so for this one here, we're going to use the MNIST dataset. So the MNIST dataset is the most important dataset for machine learning in terms of its history, right? So it's the first task which was pursued by researcher, which was that identifying handwritten digits. Okay, so there are 6,000 images. They are 24 by 24, so that the data size is 700 and something, 748. And then, so the dimension is pretty large, and each point in this 700 whatever vector, it's a number between 0 and 255, which correspond to the black and white intensity. Okay, so the images are grayscale. So 0 means completely black, 255 means completely white, and you're asked to apply k-means to this data set with the purpose of seeing if you can recover the labels. Okay, so the labels are the digits from 0 to 9. You apply an unsupervised learning approach, and you hope that your unsupervised learning approach will be able to recover the labels. Okay, so if you look at which data is clustered around a certain cluster, the data clustered around that centroid should all be the same digit. Okay, so you are reversing the use of the data set in that sense. Okay, so these are 6,000 images, right? So when you're testing out your algorithm, don't start with the 6,000 images at once, right? So make sure that you write the code from some smaller class and then you move to the largest one, right? So remember that the complexity of some of the operation in the challenge will be very large. So you apply to the whole data set, then you're going to make a disaster. So what you do is that you take a portion of the data set, you subsample it to, let's say, 1,000 images, and you just work with that. And once you have a code which is stable, then you run the code for larger images. Okay, this is not a deep learning class. This is a machine learning class. So it is not expected for you to wait, let's say, 5 hours for your code to run. Okay, so you can get very decent results with a code that runs in 20 minutes. Okay, the code that runs in 20 minutes. So here, the learning goals are as follows. So first of all, understand the basics of the algorithm. And by this, I mean that you implement it from scratch, okay? So there is an implementation of k-means in Python, and the implementation does incredible things because, of course, it's a very high-level implementation. So there are many algorithms that have been covered in the literature that are baked into that k-means solution. But of course, you cannot use it, right? Otherwise, you will not be learning anything. Then we're going to play around with the representation of the data. We said already that not all data is equally important, and it's very important that if somebody gives you a certain data set, then you explore the data set in order to figure out which features are the most important ones. And here in the MNIST data set, you can imagine the spatially, right, wherever it's in the edge of the image is not very relevant, because at the end of the images you just have the white color, right? So it's understandable for you that that if you had to crop, for example, the top and the bottom bits of the image, then the results of the algorithms will only implement because the information is preserved, but the dimension has been shrunk. But there is a neater trick, which I hope you're gonna figure out here, where you move to some other domain, right? You move to the frequency domain. And in the frequency domain, the representation of the data is even more sparse than in the original domain. The next part is to understand what is the quality of the clusters, because I think you guys already saw this with the last. I mean, you must have seen this already in your experience, that if you run k-means give you a certain clustering, and then when you plot the clusters, what happens is that there is no specific pattern in the data, and what k-means does is just dividing a cluster in dividing, let's say, the data in half according to some equal splitting of the data, right? So it's important that once you get the solution for k-means, then you have the tools to understanding what is the quality of the clusters. And in this case, there are few ways of testing this. And of course, some of them are unsupervised. Okay, so you can just see, let's say, what is the stability of the clusters if you are across different initialization. But since we also know what is the true label of the data, so we know that there are digits between 0 and 9, we can also check the cluster purity. So we can check how many of a certain digits are present in the cluster, and we can say, oh, this cluster is a majority, the number 7. So if I find any other digit which is not a 7, then that's an impurity, and I can see my clustering algorithm, which performance it has in terms of actually correctly labeling the data. Then something fun will be hierarchical solutions. So it is very easy to do k-means clustering at one level, but sometimes it is much more informative to have a multi-level k-means clustering. So you divide the data first in a first set of clusters, and then in a second set of clusters. And in the case of the digits, it's clear what you want to recover, right? So there are some numbers that have circles. So think about the 0, the 9, the 8, right? And there are some numbers that have curves but not line. Think about the 3. Think about the 2. What else? 4 is then there is like somebody that has a vertical line, like the 1 and the 4, and I think that's it. So I want to see if you guys can recover this hierarchical clustering, in which you have a first level that, let's say, it focuses on the number of circles in the number, or the number of curves in a certain digit, and then in the second level you identify the exact digit, and then understanding what is the role of the distance, okay? Because k-means, as we saw it in class, was for L2 distance, okay? So L2 distance, we love it because L2 distance can be optimized very easily. So the computation of the L2 distance, it's a very easy computation. And so it's tempting for you to think that calculating distances is always a low-cost operation, okay? But actually, this is not the case. There are many types of distances, and there are some type of distances that are computationally very heavy. And this is something that you have to take into account, because when the computation of the distance is computationally heavy, then you have to reduce the number of iterations of your k-means clustering. And so in the initialization of the clusters, it's much more relevant than in the L2 case, because you cannot iterate so many times. And which choice do we check? Which choice of distance do we have? The edit distance. The edit distance is the number of insertion, deletion, and substitution that will bring one string into another string, and the complexity of the edit distance, it's cubic, okay? So you can imagine that if you have to apply this edit distance to sequences of length 700, then the computation of the distance is much more involved than the L2 distance. So then you should be able to understand that with this trade-off between the complexity of the clustering, or of the distance evaluation, then you have to do something smarter in your cluster initialization. Okay, so here the first setting, right? So we have k-disjoint clusters. Within the clusters, we choose the centroid as the one that minimizes the distance between the points in the cluster and the cluster representative. So K is the cluster. I is the index that operates over the clusters, and then we iterate over these two steps. We say that we assign a point, the label of the entry I in the dataset at time t, xi, as the label corresponding to the closest cluster. So we minimize a cluster. The cluster index is the distance between the point and the cluster. And then there is the update step, which is the step in which you take the new cluster representative to be the average of the points that have been assigned to that cluster, to the centroid. And then you iterate across these two steps until you converge to somewhere. And the initialization, of course, it's a random initialization. So just 2 lines of code. Okay. Of course, even in the simple formula, many things can go. Even a simple formula can hide some very complex matters. First of all, initialization, right? So you can imagine that if you initialize the cluster centroid in different location, a different iteration, different runs of the algorithm, you're going to get to different clusters and different labeling. So this is something that you have to take into account, because of course you don't want to repeat the algorithm too many times, and you want to be sure that you have a good choice of the centroid, the initial centroid, so that you don't waste too much time in computation. The other big issue is k, the choice of k. Okay, so you can imagine that if you don't have a very good choice of k, then many things can happen. Okay, you can have clusters that remain empty. You can have clusters that split, let's say a true cluster, like a true latent cluster, into 2 subclusters, and so it is very difficult to initialize k properly. Okay, so in the case in which we are operating now, which is the one with k means, we know the k is equal to 10. But if you didn't know where the data comes from, or if there is some specific latent representation of the data, then you will have no reason to imagine that k is any particular value, right? So you have to figure out what are some good algorithms for choosing k, some good metrics for choosing k. Distance computation is the real bottleneck, right? So you can see that computing the Euclidean distance, let's say, takes sort of n, okay, where n is the size of the data. So if you have k centroids, then this the computation of the distance computation scales as n times k, and so as if you double the number of centroids, then you double the number of computation. So very tough. Beyond anything that you do beyond L2 gets pretty complicated. Okay, so because you can imagine that this step, beyond L2, it's not very easy, right? So how do you choose your centroid representative as the average of the other elements if this is not L2? This is true only when you're in L2. If you're in a different L, then this step will need to be modified. And also feature scale, right? So we said, for example, in the case of this MNIST data set, you can imagine that the information that each point brings, it's very limited on the edge of the image, and then it's much higher in the middle of the image. So of course, you will want to keep the representation as small as possible so that you don't waste too much computational resources. So if you have categorical data, this is problematic. Imagine that some of the features is whether the person is a student or not, or some of the features are the occupation, right? So how can you do clustering when you have categorical variable? And then clustering is not robust, right? So the algorithm can return different solutions for different initialization. Yeah, and you don't know how this can be generalizable across different populations. Okay, so let's move forward. So the dataset is the MNIST dataset. We have 6,000 images. And what something you can do is to reduce, for example, the initial labels, right? So if you just take the labels, if you just take 4 labels, then you will get a much smaller data set, right? So 600 times 4, so 2,400. So you just simplify the data set, and you can only label with this. And remember always, right, that the label, okay, it's only there for you to evaluate the quality of the cluster. Okay? You cannot use the label. during your clustering algorithm. Otherwise, there is no point. Okay, so again, I don't want you guys to just use the implementation in Python. Otherwise, there is no point. So just write these functions for me. Okay, so you compute the distances. That's the other thing that I want you guys to realize, that you have to vectorize. You have to matricize your operations. So when you compute the distance, you always compute the full distance matrix so that you can use some acceleration, some smart acceleration to compute the distance matrix. Then you have the cluster assignment. So this is where you do minimization operation. So it should be clear to you the minimization operation takes n log n complexity, because this is, again, equivalent to sorting. So this update centroid, again, in the L2 case, it's pretty easy. If you have some other case, you have to think how to do this, and then the k-means just operates everything, and then compute objectives is where you bring in the labels and the clusters, and you see how you see different measures of purity there, and then you're going to have a train test evaluation. Okay, so when you take your data, you're going to split your data in 80% training and 20% evaluation, and you're gonna measure the performance not on the train test but on the test set. Let me ask. So this splitting between train and test, it's okay, yeah? The splitting between train and test is clear? Let's see. Yes, no. Please respond in chat, guys. Yeah. Otherwise, I can spend some more time on that.
So we have to find the data set by ourselves, right?
It's in Python, yeah, just in Python.
Okay.
So if you do this, right? So the data set is because it's so popular, right? It's already there in Python, yeah. Can do this, right? Load mnist functions in Python. Let's see. So you see the data set is already there, right? So the data set is there. Now it's 70,000. Well, okay. So that's how you import it from Keras, okay? And then you do the train and test. Is this the train and test split clear to everybody or not? Can somebody tell me? Is there somebody for which is not clear, the train and test split? Guys? Okay. So the splitting is going to be 80-20. Then this is the whole data. So the training test is 60K. Okay, good. I thought I was confused. Okay, and then 28 by 28. Sorry, guys, I thought it was 24 by 24. And so the total size is 754. So here, then you split it into train and test for the X and Y label. Then with matplotlib, you do some showing. Okay, so these are represented as matrices. So when you do this IM show, you are representing the matrix value, right? So the data comes out to you as a matrix, and then you're going to vectorize it and then do clustering on the vectorized one. But if you do this IM show, then this is a heat map plot, right? So it's representing it as a matrix, and it's representing the 0 as black and the 255 as 1. So that's how you do it. And then what you do is that you normalize the data. Oh, no, I was talking about fashion mnist. Then what you do is that you normalize the data. And this is machine learning. So what you do then is that you normalize the data. Okay, so you normalize the data between 0 and 1. Yeah. So you see this the data set, guys, right? Good. Yeah. So I mean, yeah. So let me finally somebody asking questions about things that about things. So let's do this. So why should you do train and test on the why should you do train and test on the clustering, right? So what is the test? How do you understand that you should use the train and test on the clustering? Like, what would you do in inference time?
Like, we're supposed to do inference as well?
Yeah, but what is,
Or-
what would be inference in this case, in your mind?
Like using the centroids?
Exactly, right. So the new point comes in, and at inference you check that where the new point has been assigned, right? So in the train test you find the clustering, and then at test time the points come in, and then you assign them to the clusters according to the minimum distance, right? So if you're done clustering well, then you are able to classify the new points with the correct labels, right? Does it make
So
sense?
we're doing it for classification, not for clustering.
I mean, it's potato, right? So the point is that, let's say that the cluster, what will be? Okay, let me give you this example, right? So let's say that you're in an ER, right? You collect all the people that go to the ER, right? And you make some clustering of them, and you don't know exactly how they're clustered, but you know that some of them have similar symptoms, okay? And you do this because maybe you're looking for some disease that you haven't detected yet, okay? Because of course I'm thinking about COVID, right? In my mind, I'm thinking about COVID, right? So let's say that the people come in and you want to cluster their symptoms, so that then once they are clustered, you can say, oh, a person from this cluster is assigned to the doctor, and maybe I'm gonna find what this cluster represents. And if I have some people that come in and I don't know what they represent, maybe it's a new disease, okay? So in the sense, you understand that it makes sense that you have some clusters. You might not know what the cluster correspond, but you can still, let's say, use this clustering during inference. Does it make sense?
Okay.
Good. Okay, so any other question about training and testing? Again, guys, I forgot a zero here. It's a 60,000. Okay, good. So 60,000 images, and we do train and test, okay? Good. So again, so if you have a for loop over your images, that is not good. Okay, so this is a numerical recipe class, right? So your submission should have no for loops. Okay, the efficiency with which you code increases tenfold when you learn to vectorize everything, right? So when you think about an operation and there is a for loop, it is your engineering duty to try to turn that for loop into a matrix operation. Okay. As we said, so once you get the data set, then you flutter the image into 784. Oh gosh, guys, I always get confused with the dimension. So 24 and 784. Then the pixel values are between 0 and 255. Usually, it's always a good practice to normalize the range between 0 and 1. And I think after challenge 1, you understand why normalizing to the 0-1 range is good. Then you run k-means for different values of k. You run it for different initializations, and then you track the objective function as an iteration. For example, try these values of k, compare the different initialization and some smart initialization that you can come up with. Again, try to be creative. As I said, like because it's only two groups, right? So, but if we were more groups, then we will be concerned that each group has a different, has a sufficiently different presentation, right? So usually whenever I write the challenges, I try to leave the challenges so that we don't see the same ways of solving the challenge for all the groups. Otherwise, it becomes very boring. Then visualize the centroids so that you can see what the centroid is capturing. And then you can show what is, for example, the closest or the two closest images to the centroid. Okay, so this is another discussion that brings to another algorithm. I'll mention it here because I'm not particularly focused as a teacher. So you see that in this update step, okay, you allow the centroid to be any point, okay? But this is very problematic, right? Because sometimes what you want to do is that you want to take the point which is the closest to this, so that if if the centroid is always so that the centroid is always corresponding to an element in the set, so an element that exists. And this is what you will call metoid. So instead of having centroid, we say that we have a metoid. So instead of the k-means clustering, it will be k-metoids. Okay, and of course, this is a very reasonable. It's a very reasonable thing to do. For example, imagine that these are books. Okay, so imagine that you are trying to capture the topic of a book. Okay, so you do some statistics over the language, you use some embedding, whatever, and then you want to get the book that represents a certain cluster the best. Okay, you cannot take an average of the books and be like, oh, this book is the average of the cluster, and then what you're gonna read, the book is not gonna make sense, right? It's gonna be a random averages of embeddings. It's not gonna be something meaningful. So if you want instead to pin the elements to be a true element in the data set, then when you find a certain cluster of books, then you can open the book and you can read what the book is about, and you can try to infer what the cluster is talking about, right? So if one book is about romance, then you can infer that the cluster is romance, and so on and so forth. Good. So here, we were discussing this point here. So you can show the closest images to a centroid, so that if you recover some explainability of the cluster, right? So even if you let the centroid be any image, you can look for the few nearest images, so that you can have an interpretation of what's in the cluster. Choice of k. So you cannot choose k in advance. You have to figure out what k is as life goes on, right? So there are going to be some things for you to look up. So one is the elbow score. One is the silhouette score, and then once you go and use the actual label, then you can look at the purity, and you can look at the stability across the different runs. Okay. Then you're going to apply the DFT. Okay. How many of you know what is the DFT? Do you know what is the DFT? Question mark? Yes, no. Yes, no. I think that's one person doesn't know. Let's see if somebody else in the group knows, so that you can explain to each other. EFT stands for discrete. So you guys haven't taken any class on, let's say, signaling system. Discrete for, yeah. Okay, so yeah, you can look it up. It's something very intuitive. So basically, the 1D version of the discrete Fourier transform will represent a signal, a discrete time signal, as a set of frequency components. Okay, and when you go to a 2D signal, then you also have an idea of 2D waves that you can use to represent images, and this is an alternative way of representing the image, and it's a one-to-one correspondence. And when you're in engineering, you're gonna study the DFT in 5 or 6 different courses. So no point of me spending too much time on this. Just remember that it's a transform domain, right? So you can imagine that the images, they live in the original domain when they're given to you in terms of intensity, and you can bring it to a different domain, which is the complex exponential domain, the frequency domain. Okay, and when you do this, it's an invertible operation, so there is no loss of information, and also the transformation from the original domain to the discrete domain, to the frequency domain, has a complexity of n log n. So it's a very cheap operation to do. And images that look very dense, information, to have a lot of information in the original domain, they turn out often to have very sparse representation in the frequency domain. So it's a domain in which representation tends to be very sparse in some sense that you're going to tell me. And so you can do this in this Fourier domain, and then you can add a weighting of the features. Okay, so here we do k-means clustering, but we have a weighting of the features, because in this frequency domain, features are going to be very sparse. They're going to be more sparse than in the original domain, and then you have to decide how do you choose this omega, and you can figure out. Okay, so you can figure out a way in which you can produce k-means clustering for a certain set of omega, and then you optimize the omega. You do k-means clustering, and so on and so forth. Should be nice. How to optimize the weights? Just choose something. Of course, you can start with some random search. Then you can try to optimize in some other way. So this is also very nice. And then path is to validate train test splits. So yeah, you can test different predetermined objectives. As I said, purity is the first one to investigate. Entropy is another good one. Stability is also a good one. So you repeat different times and you see how the stability goes. And then the last one is to train across different train test split ratio. Okay, so usually we like 80-20. So this is the usual. Like if you approach a problem, you have no reason to believe that you need to play around with train test splits. We'll just choose 80-20. And here you can see what is the performance that you get having different splits. And then we have the hierarchical one. So as we said, we have a first level and second level of labels. But this should be fairly easy, right? So you have one implementation of k-means, and you run it first for the whole image for a certain k, and then you run it inside each cluster for another k. Just see what you can obtain. And then the last one is for using the edit distance, okay? So you can represent the data in binary. And then once you represent in binary, then you can apply the edit distance. So a certain level of complexity, right? Because the image is a 2D image, so you have to decide how you're going to define the edit distance of a 2D image. Of course, you could simply vectorize and then use on the whole vector. That's not going to make much sense. I'll let you explore how you should define the edit distance of a 2D image. What is the meaningful application? And then you can do the method which we discussed before, because as we said, so if you do if you use edit distance, then you cannot use averaging, right? So the averaging operation, it's not trivial, okay? Because you have to find the element at minimum minimum edit distance from all the elements in the clusters, and the complexity of this is beyond cubic, right? So it's cubing multiplied by the number of elements in the cluster. So it's very difficult. And then that's it. Okay, so this is very difficult task in general. So there are many things that you can improvise. Hopefully, you can do a very good job. And yeah, of course, don't rely too much on ChatGPT for this task, because this is Gen AI proof, right? So if you ask Gen AI, it's not going to be able to give you any good solution. So don't trust ChatGPT or Claude or whatever, or Gemini over this task, because it's going to make a mess. Okay, so as a teacher, we also have to be able to give you some Gen AI proof, Gen AI resilient tasks. Okay, and then the deliverables are like for the last challenge. Okay, very good. Any questions on this, guys? Again, sorry for giving to you late, and yeah, next time keep pinging me, guys. Life is very busy, so if I think I've done the task and I made a mistake in the task, yeah, that's anyway. So apologies again. It will not happen again. Don't worry. I don't know why I missed the messages also for Slack. So yeah, again, apologies, and we will not redo this mistake again. Okay, any questions? Otherwise, we take a 2-minute break. I'm gonna see you back at 4. Okay. Okay, guys, let's go walk around, drink something, and then we move to the next part of class. Okay. Okay, very good, guys. We're back at 3. We start in 1 minute. So we're gonna finish the part on matrices today, but then we can move toward SVD. My computer has to update again, so I lost the ability to share only one tab. I have to share my full screen again. Apologies. Apologies, guys. I don't know why. I can just share it. Oh, now I can see the window. Okay, good. Okay, so where's the full screen? Command Enter? No. Where are we? How do we do full screen? View full screen mode. Okay, good. Remember the last time we were doing matrices, right? So we describe matrices very briefly. We talk about this idea of sparsity, right? We say that many matrices in machine learning they have a very large size, but actually the number of non-zero elements is very small. And we have a special way of studying and treating these elements. We really like sparse matrices. When we describe matrix operation, right? So this was a fairly standard stuff. Just a reminder, we give the example in which a matrix represents a graph. We go down, concatenation of matrices and so on. This was the example when we represented a filter, right? So a moving average filter. So we said the convolution is used for doing filtering. We said that convolution is also a band matrix. Then we did Van der Monte matrices, which we say represents a polynomial. Okay, so these are the t's are the points in which the polynomial is evaluated. So if you want to evaluate a polynomial of a certain set of coefficients over different points, you can represent the evaluation of the polynomial as a times x. Very good, very natural. Then discrete Fourier transform, this is the one that we discussed today. We say that the discrete Fourier transform is a special case of the Toeplitz matrix. Again, this is a complex matrix. There is a lot of theory to be discussed here, but usually you do this in the signal and system class. And there's also a class on image processing and a class on linear time invariant systems. So I think you will see this object in many different classes. But the idea is that this omega being equal to the square root of to the exponent of with a complex exponent, right? And e to the power of j, where j is complex. It's a beautiful object that all engineers love. And being an engineer, it's really understanding what is the meaning of this object. We discussed affine functions, which are like continuous functions where the coefficients sum up to 1. Then we did affine approximation. Okay, so very good. You remember this. And then complexity goes here, and then we move on from there. Okay, good. After this, we're going to discuss inverses. Okay, we're going to discuss inverses. Just a second. Discuss inverse of the matrix. Sorry, just a second, guys. Just a second, guys. Just a second. Where are you? Come down. Orthogonal matrices. Computer, it's a bit slow. Save. And now we have to share this tab. We have to share this tab. For some strange reason, I lost the ability to share. Come on, be nice to me. Be nice to me. tell me that I can share this. Okay, good. Sorry guys, it's when there is an update, I don't know what is the, yeah, it makes it unstable to share a single tab. Let's see if it starts. You can see it, right? Now, can you see? You can see my slides. Now,
No.
okay, let me try again. Oh, damn it. Let's see if it's okay, now it starts. Good. Okay. Good. So the path where we're going now, we're going toward matrix decomposition. Okay. So we want to get to the algorithm for SVD, okay, single or PCA, principal code point analysis. Okay, so in order to get there, we have to understand what does it mean to decompose a matrix into a product of other matrices. So you have a certain matrix A, and you want to write the matrix A as a certain P times Q, and you can choose different properties for this P times Q in order to impose some structure on this decomposition. So that if you look at P alone and Q alone, then there is something that you can learn from the way in which the matrix is decomposed. Okay, so in order to get there, we have to do a few things. So we start with orthogonal matrices. So let's see what it means for a matrix to be orthogonal. So orthogonality is established in a set of vectors. So as you remember probably from your high school days, two vectors are orthogonal if they have each norm 1 and if their inner product is equal to 0. Inner product here we write it as a row vector times column vector. And so if instead of only having two vectors we have n vectors, then we ask for each of these two properties to hold for all possible pairwise vectors. Here some nice example of orthogonal vectors. So if you stack orthogonal vectors into a matrix, so that you stack them row-wise or column-wise, then if you do this A transpose A, then you will have a matrix with orthonormal columns or rows, depending on how you constructed it. In this case, we have orthonormal columns. So this A transpose A will have that all of the off-diagonal elements will be orthogonal, so the inner product is equal to 0, and only on the main diagonal we have a vector time itself, and since it's the norm is equal to 1, there it's orthonormal, we obtain a nice identity matrix. Okay, good. Then we want to see, I mean, what we can do with this matrix, right? Is it something interesting that we can use it for? So remember that this is an m times n matrix, so this needs not to be square. So the type of operation that we can do is sort of limited by the fact that this matrix, it has a generic shape. But of course, what we can do is that we can take the product of AX and AY. So AX is again a column, and AY is going to be a column. And so when you take the product of the two, this is equal to the inner product. So in a sense, what you're doing is that you're taking a linear function of x, and you're taking the same linear function of y, and you're showing that the inner product of the operated elements is the same as the inner product of the original ones. So this is kind of surprising, and it's very important, right? And it's said that matrix time vector products, they preserve the inner product. Okay, then we also preserve the norm. So if you take the A times X, you write it again as an inner product, and since it's an inner product of a matrix it's an inner product of a vector by itself, then we preserve the inner product, and in this case the inner product is equal to the norm. Okay, so orthonormal matrices, they do a very nice thing for us, and they preserve the inner product and they preserve the norm, but they also preserve distances. Okay, so if we preserve the norm, then this is simply the matrix times the distance vector. So we are also preserving the distance, and they also preserve angles. Okay, so remember that AX and AY are still vectors. So if we do the arc cosine here, basically we preserve the inner product, we preserve the angle, so everything is preserved. So the angle is also preserved. So these orthonormal matrices, they are very, very nice. Okay, they have a lot of nice property that we like. Now we can discuss about left invertibility. Okay, so usually when you guys see matrix inverses, you don't distinguish between left and right invertibility. That is because usually you don't want to get into this into this topic as a high school, but now you can expand your horizons. So we say that A is left invertible with left inverse A transpose if A transpose times A is equal to the identity matrix. Okay, so you see that since the product is not commutative, you can have that something is invertible on the left-hand side or on the right-hand side. So if A is linear independent columns, then A times I is equal to 0, and implies that A transpose A times X is equal to X, which is equal to 0. Okay, so yeah, so if you have a linear independent columns, then the only way for this product to be 0 is for the X to be 0. And of course, A needs to be tall or square. Because yeah, this doesn't work if you don't have a tall or square matrices. Very good. So I guess I'm losing track. We're going this way. Good. Orthonormal matrices. So a square matrix with orthonormal columns is called orthogonal. Before we saw the gram matrix, which could be any shape. And we said that we have a left invertible if it's tall. You can imagine if it's right invertible, it has to be fat. But the fat and tall matrices, they meet into square matrices. Again, I should say tall and wide, but historically I was told fat matrices. It's not very accepting of people shapes. Anyway, so so the matrix is orthogonal and it's non-singular. So if A is orthogonal, then A, if it's invertible with inverse A transpose, so A transpose A is equal to I, and A square means that A transpose is equal to A times A. A transpose times A is equal to A times A transpose, which is equal to the identity matrix. And A transpose is also an orthogonal matrix. So if you take an orthogonal matrix and you flip it of 90, then you get also an orthogonal matrix. The rows are orthonormals, and also the columns are orthonormals. Okay. So note that if A is an M times N, it has orthonormal columns of M greater than N, then A times A transpose is different from the identity. Okay. So so if M is greater than N, means that the matrix is tall. Right? So when you take the transpose, you will have that you have the first submatrix N times N, which is equal to an identity, and then you'll have a bunch of zeros. Okay, so imagine that you have a tall matrix, right? So you take the tall matrix times the wide matrix, right? So of course, you cannot have M orthogonal vectors, right? So you run out of dimension to do this. Okay. Good. So the permutation matrix is a special case of an orthonormal matrix. And so in the permutation matrix, you have that you have only one non-zero element for each row and one non-zero element for each column. And if somebody gives you a certain reordering, right? So you start with pi, which is from 1 to n. Then you apply this permutation matrix. The effect of the permutation matrix, is to change the order of the elements without changing the value of the elements. And permutation matrices are all orthogonal, okay? And it's also intuitive for us to understand because if you have a certain change of order, right, then when you take the transpose, you invert this ordering. So it's very intuitive to see that permutation matrices are orthogonal, and the A transpose is equal to A to the minus 1, okay? Because you change the order and then you invert this change, so you end up with the original matrix. Yeah, just some example, blah, 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 very easy. We move on. Plane rotation, okay? So If you have a vector x and you want to rotate this vector of a certain coefficient theta, then you do a rotation is like as follows: cosine of theta minus sine theta, sine of theta, cosine of theta. Maybe you also memorize this in school at some point in your life. And when you generalize this to higher dimension, then things are very complicated. So, for example, this rotation in R3 here means that the coordinate 2 is left unchanged, but coordinate 1 is rotated. So you're rotating on the 1,3 plane, right? So if this is your x, y, z, whatever, you're just rotating on an hyperplane there. So then we said, what is the reflector? The reflector is this. Remember that we had an interpretation of the reflector. We had an interpretation of the reflector on 2D. So when we go to a reflector in higher dimension, this still works out, right? So this A now can be of any dimension. So if you take a matrix A, the intuition of the reflector is this, okay? So we saw it in 2 dimensions last class, but now we have it in 3 dimension. So in this case, we have an hyperplane H, which is defined by the equation, the coefficients of the plane A transpose U, means that is the hyperplane which is perpendicular to the vector to direction A, and so the reflector is the matrix that brings you from here to there. Okay, good. Some exercises, I'll leave it up to you. You know where to find the slides. This is to show that if we take a projection X on the plane, okay, then this corresponds to a point Y, which is on the other side of the hyperplane as we have it here, okay? So X, Y, Z. So A is the direction of the plane, so this is direction A, and this is how you obtain the reflection. Very good. So in this case, you want to show that the distance between X and Z is the same as the distance between X and Y. Also the opposite holds, and so they must be equal. Okay, so moving on. So the product of orthogonal matrices of equal size. So let's say that we have a matrix A, and what happens if you take the product of orthogonal matrices? Then the product of orthogonal matrices is also an orthogonal matrix, and this is easy to see because when you take A transpose A, in a sense, you flip the matrices, and then you have the K cancel with 1 cancel with 1, 2 cancel with 2, K cancels with K, and then you end up with an identity. So this gives you some nice idea on, let's say somebody gives you some data, right? You could use this stacking up, this property of being able to stack up orthogonal matrices to do something interesting, right? Linear equation with orthogonal matrix. Let's say that you have a linear equation with orthogonal coefficients matrix A of size n times n. Then you will have the equation corresponds to AX equal to B, and the solution will be A to the minus 1B, which is equal to A transpose B. So you will be able to solve it. And in terms of computation, the computation is 2 n square flops for the matrix vector operation, as we saw last time. But sometimes you have some saving in computation if you have some special matrices. Of course, permutation costs 0, right? Permutation, it's not a concern, right? Because you're just reordering the elements, so you can sort of hard code this. If you have a reflector, actually this takes only n flops, so A is fixed. Okay, so the direction is flipped. If you have to perform the reflection, then it takes only n flops. And as we shall see, this is very important because when we do QR decomposition, which is coming up next, then we will use the reflector in order to bring down the complexity. And plane rotation has an order of 1 flops. Okay, so plane rotations are also very efficient because the matrix has a very large dimension, which depends on the angle theta. But in general, you actually have only one parameter that is driving the transformation. So there are some smart ways of just writing the translation vector so that the complexity goes down to 1. Okay, so now we go to tall matrices with orthonormal columns, as we have hinted. So now we have a tall matrix with orthonormal columns. So we have imagine a tall matrix, right? So in a sense, on a tall matrix, it's easy to have orthonormal columns because you have many dimensions that you can use to establish orthogonality. Okay, so AT is the left inverse of A. Okay, and this is A transpose A equal to I, but A is not right inverse. It has no right inverse. Okay, so there is no matrix. So you cannot have the A times A transpose equal to I. Cool. So we'll give an interpretation of this later. Intuitive, it's clear, right? Intuitive, it's clear because, yeah, if you have a tall times a flat, you don't have enough vector pairs to have orthogonality. Good. A span is a collection of vectors in the set. So if you have a set of vectors, A1 to AN, you define the span of the collection of vectors as the set, as the plane constructed by all the possible linear combinations. Okay, so you have these vectors, and you decide any linear combination of this, and this will generate the span. Okay, and the range of the matrix A is the span of its column vector. So if I take a matrix A, what do? That I take all the columns, and then I consider them as linear combination. So I construct a span of the column space, and so this is called the range. Okay? So let's give an example. So we have the tall matrix here. What we do is that we consider all the possible ways in which we can construct another vector, 3 times 1, which is a linear combination of these elements. So of course, here we have that we can parameterize the transformation as x1, 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 x2, x2, x2. So we have x1 plus 0, because there is no element here. Here we have x1 plus 2x2, and here we have minus x2. So any point that satisfies this, any vector that can represent it with any choice of x1, x2 corresponds to the range of the column space. Then if A is an m times n that has orthonormal columns A1 to AN, then the vector A times A transpose B is the orthogonal projection of an m vector B on the range of A. Okay, so now we have the matrix A, we have vector B, and we look at A times A transpose B, and this corresponds to the projection, to the orthogonal projection, right? Which is we go along the direction of the direction here, right? We look at for the closest point to the plane. So xat, which is equal to A transpose B, satisfies that A times xat minus B is less root of the AX plus B for all the points on the plane, and so this is always true. And then we call the residual B minus A transpose B. So the residual is this difference vector here. Okay. The proof is here. Is not it's not a problem. You can go through this by yourself. But once we have this, now we can have an orthogonal decomposition as follows. So we are given a vector B, and we want to decompose the vector B into a Z plus Y, where Z is in the range of A and Y is in the orthogonal space of the range of A. And this is very nicely obtained as follows. So we said that the projection Z, so this is in 3 dimensions, right? So this is the vector B. So these elements here is A times A transpose times B. So this Y here will be B minus A times A transpose B. And everything is cool as we expected. Okay, so the orthogonal vector is this Y, and the Z is the one is the other part. Okay, so now if we let U and V be 2 orthonormal vectors, what we can show is that I minus U transpose minus VV transpose can be rewritten as follows. And if A is an m times n matrix with orthogonal columns, then we can show that this is the reflector equation, right? So this is why doing reflector is very efficient, because I minus I transpose decomposes the product of I minus the column-wise inner product. Now we move to complex matrices, not a big deal. So just remember that now instead of transposition, we always have Hermitian complex conjugate. So we have to change the sign of the complex part of the matrix. Unitary matrices, everything goes through. Discrete Fourier transform, a problem, because this was a complex matrix to begin with. Then the Graham matrix, remember this is the one that we saw before. And yeah, that's it. Good. Any questions on this? Otherwise, we move on. Now we can finally go to inverse matrices. We can discuss more about inverse matrices. Okay. So here we share this one. Full screen. Okay. Okay, very good. So matrix inverse. So we discussed the left inverse. Now we're going to discuss the right inverse. And then the linear independence is there, and then we can define better our non-singular matrices, because we mentioned non-singular before, but we didn't specify too well what non-singular means. Okay, so we see the left and right inverse for these orthonormal matrices, and this was nice, right? So now we want to do it for a generic matrix. So A times B is different from B times A in general. So that's why we need to distinguish a left inverse and a right inverse. So the left inverse is the matrix X.
It's black screen again.
Why does it do this to me? Why does it do this to me? Let's see. Thank you, Nafal. Let's see if it starts over. Yeah. Okay, good. So left inverse and right inverse. We're good. Okay, so we said that X is the left inverse of A if X times A is equal to the identity matrix. And if A is left invertible, it has at least one left inverse. And the right inverse is X is the right inverse of A if A times X equal to I, and A is right invertible if it has at least one of the right, at least if it has at least one right inverse. Notice that invertibility in the nice square matrices that you guys saw before means there's only one inverse matrix. But here, when we have left invertibility or right invertibility, you can have a bunch of inverse matrices, right? So it doesn't need to be one. So we lost uniqueness. Some example, no need to worry, right? But maybe we can discuss this. So A is tall and B is wide, right? So A is left invertible, and these are two possible left inverses, and B is right invertible, and these are two right inverses. Okay, so if you think about dimension, right? So this is a 3 times 2 matrix. So this is a 2 times 3 matrix. So when you multiply them together, you get a 2 times 2 identity matrix. And of course, in a sense, right, you can choose 6 elements, right? So that you have to fix 4 element, right? So if you think about it this way, right? So here you have 6 elements that are fixed, okay? And you want A transpose A. You want, let's call this B or X. You want X times A to be equal to the identity. Okay, let me start again. A is this 6-element matrix, 3 times 2. So the X is going to be a 2 times 3 matrix, right? And their product is going to give us an identity matrix, which is the smallest dimension that we have. And we have 2 dimensions. So the product X times A must be equal to an identity matrix of dimension 2. So in a sense, intuitively, right, we can choose 6 elements for the matrix X, right, so that we fix the 4 elements of the identity of the 2 times 2 identity matrix. So in a sense, we have a system of equation where we have more unknowns than equation, so we can find many solutions to this problem. Okay, same thing for right invertibility. Okay, so the X is tall, and in this case we have that it is a 2 times 3. So this is a 3 times 2. So this is going to be a 3 times 3 matrix. And in this case, we are lucky, right? There's this matrix has 2 zeros, right? So when we get the 3 times 3 identity matrix, there are some choices, right, where we can still obtain an identity matrix, which is 3 times 3. Okay, good. So this case was nice because in a sense we had more equation than unknowns, more unknowns than equation. Sorry, guys. This case we didn't have that condition, right? The unknowns is equal to we have 6 elements here to decide, and the inverse that we are looking for are 6 elements. We don't have extra equation, but we're lucky here that there are some zeros and lots of ones, so we can find multiple solutions. Good. So just simple properties. If we have that the matrix is m times n, then the inverse must be n times m. If X is a left inverse of A, if and only if X transpose is the right inverse of A. This is easy, right? So if we have to transpose, then the transposition is going to flip the matrices, right? So A transpose times X transpose is equal to X times A transpose. X times A is equal to the identity matrix. So if you transpose the identity matrix, we have the identity matrix. So everything is nice. So if X is the left inverse of A, if and only if X Hermitian is the right inverse of A Hermitian. So same thing with the complex matrices. So if A has a left inverse and a right inverse, and they are equal and unique, then we say that this element becomes the blessed A to the minus 1. Okay, so X times A is equal to I, A times Y is equal to I, and X is equal to X times A times Y is equal to X times A times Y, which is equal to Y. So then really X equal to Y can be called A to the minus 1. Okay. So a matrix is invertible if it only is this, if and only if the inverse exists. So this is the matrix A, and this is its unique inverse, A to the minus 1. Good, good. So now we connect matrices to linear equation. As we said, we can imagine that AX equal to B is a set of linear equation that you deconstruct in this way. And if you think about this, we know that depending on the number of unknowns and the number of equations, this system can have a unique solution, no solution, or infinitely many solutions. So now that we have set up the invertibility condition for matrices, then we can solve linear equations using matrices. So AX is equal to B means that X is equal to the left inverse, right, times A times X, which is equal to big X times B. So there is at most one solution, and the solution must be equal to X times B. If we have a right invertible matrix, so if X is the right inverse of A, then this happens. So there is at least a solution. And if we have an invertible matrix, right, which is the left and right inverse are the same, then AX equal to B as a unique solution, which is A to the minus 1B. Okay, so we saw the case where we have at most one solution, at least one solution, and then we have the exact invertibility case. Good, back to linear independence. So we saw linear independence as linear combination of vectors. Of course, we are happier to see linear independence as a linear product being equal to 0. Yeah, so a set of vectors is called linearly independent if the only linear combination that yields a 0 is the linear combination with all coefficient zeros. And if we want to write this in matrix notation, means that AX is equal to 0 if and only if X is equal to 0. So if A are linearly dependent, it means there exists a choice of the coefficients, so that the coefficients are not equal to 0, they're not all equal to 0, and this linear combination is equal to 0. So, which means that at least one of the vectors, it's a linear combination of all of the other vectors. So that's why we say they are not linearly independent. Okay, and then you extend this to sets. Okay, so you can have a set of any dimension. And by convention, we say that the empty set is linearly independent. Not very relevant, but what can we say? Yeah, just some example here. Yeah, we don't need to go through this. Now, when we start going to connecting, the idea of rank and the idea of the idea of ill-conditioned matrices coming up. So let's say that we have n vectors, and they are all length m. Then we have at most m vectors that are linearly independent. Then n is less or equal than m. Okay. If m times n is a matrix that has linearly independent columns, then m must be greater than n. Which means that if A is wide, then the columns are linearly independent. If A is wide, the columns are linearly independent, means that the homogeneous equation AX equal to 0 has a non-trivial solution. So again, the trivial solution will be the vector all x. Okay. So if the matrix is wide, then we can find a solution AX, which sets everything to 0. Okay. If an m times n matrix has linearly independent rows, then m must be less or equal than n. If A is tall, its rows are linearly dependent. Okay. Okay, so this is saying that, again, connecting to the number of equations and the number of unknowns. If we want to have linear independence, right, means that we are looking for a non-trivial solution of AX equal to 0. So we have to have more unknowns than the equation. Otherwise, we cannot find this. Good. And now we get to the idea of singular matrices. So if a square matrix A has the following properties, these properties are all equivalent. I'm checking the time so I don't go long like last time. So A is left invertible. The column of A are linearly independent. A is right invertible, and the rows of A are linearly independent. Okay. So if a matrix is square and has these properties, then we call the matrix as non-singular. And a non-singular matrix means that it's invertible. Okay. So the proof is like this. We're not going to do it because this is for your own interest. So the proof follows this circular. I don't know if you guys have ever done it. Maybe you will do it in some other class, but anyway, we're not going to do it here. Some example of linear dependent independent matrices. And then we go back to our beloved van der Waals matrix. The matrix is non-singular if AX equal to 0, if and only if X is equal to 0. So it means that AX means that we are evaluating the polynomial, right? And the polynomial at this point at T1 to Tn has to be fully 0. So so it means that all these evaluations are 0, means that they all must be roots of the polynomial. So the polynomial has to be of degree n minus 1 or less. But we know that a polynomial of degree n cannot have more than n minus 1 distinct real roots. So in order for this to hold, the x must be equal to 0. Otherwise, this will not be possible because we cannot have this many roots in the polynomial. Okay, so the van der Waals matrix can be 0 only if they are all only if x is equal to 0. Okay. So transpose and conjugate. Now we have a definition of A transpose A conjugate. A transpose to the 1 is equal to A to the minus 1 transpose. Okay. So you know the relationship between inverting a matrix and transposing the matrix. And if A and B are non-singular and of equal size, then A times B is non-singular with A times B to the minus 1 be equal to B to the minus 1, A to the minus 1. Okay, very nice. So we still have this flipping that we have with the transposition, but now it's with inverse. Okay, now matrices with linearly independent columns. This is our gram matrix. We have a linearly independent columns. We can also do it with complex. So just the parallel of what we did before. Then we have a non-singular gram matrix. The gram matrix is non-singular if and only if E has linearly independent columns. So now we link non-singularity with the number of linearly independent columns. The proof is here for you. And now we get to the pseudo-inverse, which is where we wanted to get. So suppose that A is an m times n matrix that has linear independent columns. Okay, so this implies that A is tall or square. Okay, because because we have to have that m is greater or equal than n. Then we cannot define an inverse. So what should we do? Should we just give up the idea of inverse? Of course, we don't want to do this. What we can do is that we can define a pseudo-inverse. Okay. Okay, what is a pseudo-inverse? And what are the properties of the pseudo-inverse? Let's see. So here we will call it A dagger, right? A dagger is equal to A transpose A to the minus 1 multiplied by A transpose. Okay, we see this and we have to believe it, okay? So we want to see a couple of things here, okay? So if m is equal to n, then the matrix is square. And if we have this many linearly independent columns, then it means that we should be able to have a regular matrix inverse, okay? So this is the first thing that we have to check. If m is equal to n, then the pseudo-inverse becomes the real inverse. And the other thing that we want to check is whether the dimension fit, right? Because if we have an m times n matrix, then we know that the inverse, whatever, left or right inverse, however we want to define it, has to be n times m. So the dimensions have to be flipped. And we have to check that this really happens, okay? So before we move forward with the properties, we can see what happens here in the formula, okay? So this is an A dagger, okay? And we do this. First, we take A transpose A. A transpose A is necessarily a square matrix, okay? So that one is good. Then we take the inverse. So now we have an inverse, and we don't know if this happens in general, but we know that we have linearly independent columns. So once we do this, we get a matrix that is invertible by definition, and this follows from the fact that A has linear independent columns. And then we have this multiplication by A transpose, which in a sense fixes again the dimension to be the desirable dimension. Okay, so this matrix exists because the Gram matrix A transpose A is non-singular because A has linearly independent columns. And A dagger is the left inverse of A. Wow, let's see if we believe it. So A dagger A, right? So the A is here, the A dagger is there. So you see that you have A transpose and then you multiply by A. But this beautiful object, right, is going to be a square matrix again. This is the inverse of this matrix, so this is equal to the identity. Wow. So the pseudo-inverse, A dagger, it's a left inverse of A. Of course, if we go complex, then nothing changes. Okay, so following these three properties are equivalent for a real matrix A. A is left invertible. The columns of A are linearly independent. A transpose A is non-singular, okay? And this is, again, we can prove it, but you'll believe me for now. Matrices with linearly independent rows, okay? So, guys, when do we finish? I don't want to, we finish at 50, right? No, can you remind me when we finish? 10. We find at 10. We finish at 10, right? Okay, good. Forget things. Okay, we finish at 10. So matrices with linearly independent rows. So now we have we can define a pseudo-inverse for a matrix with linearly independent rows. So suppose that A is an R times M matrix with linearly independent rows. Okay. So this implies that the matrix is either wide or square. Otherwise, we will not be able to have linearly independent rows. Okay. Which means that we can also define a pseudo-inverse for this object, which is again A dagger, A transpose, and then we have A times A transpose to the minus 1. So A transpose has linearly independent columns. This means that the Gram matrix A times A transpose is non-singular, okay, because linear independent rows. So then this guy here can be inverted, and then we again, in a sense, adjust the dimension multiplying by A transpose, so that the product of this object is N times M. And then, as the pseudo inverse before was left inverse, you can imagine that in this time we have the right inverse. So we have A times A dagger is the right inverse. So the A dagger comes from the right. And this is true because, again, we have the matrix A. So this A transpose, the A times A transpose will give you a square matrix. And then you have this -1. And then when you take this product, this goes to identity matrix. Okay. And then if we have a complex matrix, we just put the Hermitian. Okay. So good. So we figured out that basically what we knew before the class was how to invert square matrices that were non-singular. But then, of course, if you look at the family of all possible matrices, there are not that many matrices that they are, that they have these nice properties, right? And we figured out that what we can do is that we can define, instead of an exact inverse, a pseudo inverse, and the pseudo inverse satisfied only half of the requirement for being an invertible matrix, right? So when a matrix is invertible, then the left inverse is equal to the right inverse. In this case, we were just happy of having either a left inverse or a right inverse. Okay, so you have to choose, you have to pick one side, right? So if you want to be a tall and wide matrix, a tall matrix or a wide matrix. Good. So a little bit of summary here. The three properties are equivalent. A is right invertible. The rows of A are linearly independent. A times A transpose is non-singular. Good. Okay, good. Let's see what we want to do after. I don't want to push too much, but we're pushing up toward the QR decomposition, which is going to be nice. Okay, we just finish with QR factorization, and then I'll let you guys go. This should be pretty neat, because finally we are getting there. We're getting to this idea that we wanted to get, which is the idea that if I have a matrix, I want to decompose it as the product of some sort of special matrix. Okay, okay, good. Let's see if it starts. View. Let's see if I can go full screen now. Full screen. Okay, good. Okay, so we close with this. Next time we're going to recover with SVD. We're going to continue with SVD. So triangular matrices. A matrix is lower triangular if all the elements above the diagonal are 0. You flip, you get the upper triangular matrix, no problem. And sometimes you want to define whether the diagonals are equal to 1. And this is called a unit upper triangular and a unit lower triangular. Okay. So if this diagonal is all equal to 1, then it's called unit lower triangular. It will become important later when we do QR decomposition. Okay. If a matrix is lower triangular, then we are very happy. Okay. Because if a matrix is lower triangular, then we can do this type of Gaussian elimination. Okay, so if we look at the system AX equal to B, then this is lower triangular. Then we know that X1 is equal to B1 over A11. Then we go and we substitute on the next equation, and we have B2 minus A21 times X1. So the solution that we had before, divided by 2, and this continues, right? So this, sometimes you call it Gaussian elimination. And so we know that that this is very desirable for us because the complexity is only n square blocks. Okay, so if you had to solve this system of linear equation, right, then it's not clear to us how we will do it, right? But basically here you can see that the complexity, right, it's n square, which is very much desirable because, in a sense, you have to take all the elements of the matrix, right, in order to suit this, right? And the elements of this matrix are n square. So how can it be the complexity of solving the system of linear equation having the same size as the matrix A? Of course, there is something very desirable, right? Because at least I have to look at all the elements of the matrix A, right? So the minimum complexity I can have is to have n square. Very logical, right? So n square is the best that we can do. There is no way that we can do best than n square, because we have to visit all the elements in the matrix A. And yeah, so with this one here, we find all the forward one, and if we have an upper triangular matrix, then things would be the opposite. Right? Instead of starting from the x1, we will start from the xn, and then we will solve upward. So this is called forward substitution, and this is called backward substitution. Not a big problem. Good. Okay. So let's see what we know about the inverse of a triangular matrix, right? So what can we say about this? So a triangular matrix A with non-zero diagonal elements. So the diagonal must be non-zero. Okay. Then it's non-singular. Okay. So the way in which AX can be equal to 0 is if and only if X is equal to 0. And if you look at the back substitution equation, it's clear that the only way in which you can have a 0 in this type of solution is that, well, here the x1 has to be equal to 0. Now we have a 0 there. And so also these elements, if the only way to be 0 is for it to be 0. Okay. So very intuitive. Okay. So okay, so the matrix is non-singular. Okay. Sorry guys. Wait a minute. The matrix is non-singular. And so we can have the inverse because it's square, right? So the inverse of A can be computed by solving AX equal to I. And I is the identity matrix. So now this one is the all zero vector, which is one in position equal to the subscript, so 1 to n. And then xi is the, remember in this notation, is the column of the column I of x. Gosh, and so it can be done very, very efficiently doing this back substitution, right? Because we will just put here, we'll just put here the values of E, right? A1, A2, A3. So this is just always equal to 1, right? And that's it. Okay, so we will either have a 1 or a 0. We solve this in the vector form, and we are all happy. Okay, so you can imagine that you are doing this n-square solution, right, for each of the vector there, and the complexity of computing the full inverse is like n cube. It's just like n cube. Okay, so fairly easy to figure this out. Okay, so now we have that this is very efficient. Having a cube as an inverter seems to be very, very good as a trade-off. Let's see what happens. Next, we get to the QR factorization, which says this: that A, if an m times n matrix has linear independent columns, then it can be factorized as follows: this Q1 all the way to Qn, and then multiply by these elements. Okay, so Q1 and Qn are orthonormal m vectors. So this is an orthonormal matrix, which means that the norm is equal to 1 and the inner product is equal to 0. The diagonal elements of this matrix R are all equal to 0. So this is a square matrix which is equal to 0. And RII is less than 0. Then we can switch the sign from here to there, so that we can have a definition in which the RII is greater than 0. And so this will give us a decomposition of the matrix A as the product of a matrix Q and a matrix I, which is unique. Okay, so if you fix the R in the diagonal to be positive, then you will have a unique factorization. Okay, so this means that if A is an m times n matrix that has linearly independent columns, then it can be factorized as A equal to Q times R, where Q is an m times m orthonormal matrix. Okay, and A sorry, and R is this element that has positive elements on the main diagonal. And if A is a square, so m is equal to n, then Q is orthogonal, right? Instead of being only orthonormal, it's orthogonal. And then we have the Q transpose is equal to Q times Q transpose is equal to I. And what do we know about the matrix R? So R is upper triangular, okay, and has non-zero diagonal elements. And A is also non-singular, okay? So the diagonal elements are non-zero, and they are also positive. Very nice, right? So we gained a lot. Why? Because since the Q is orthogonal, then we have this beautiful thing that we can just take the transpose instead of doing the inverse. And when it comes to R, right, we just said that this upper and lower triangular, they are very easy to inverse, right? So it seems that we are in a good shape for solving the equation very efficiently, okay? Because this inverse has n cube, and this other inverse has as a transposition, so as complexity is 0. So it seems that we are in a very good boat for doing the inversion. So just some example, because sometimes it's very difficult to believe that things have really work out the way they are. But you see that we are decomposing this matrix into this orthogonal matrix. It's easy to see that this is orthogonal because, well, yeah. So this is a matrix that you know. So this could be an FFT matrix, for example, or DFT matrix. Doesn't matter. And this is an upper triangular matrix. Okay. So this is the Q matrix, and this is the upper triangular matrix. Very good. Good. So sometimes it's often easy to easy to define the factorization of A for a generic matrix A as Q times Q tilde R times 0. Okay. So A is equal to QR. Then the QR factorization is defined as before. And Q tilde is an M times M minus N block, which is all zeros, right? And the matrix Q times Q tilde is an M times N orthogonal matrix. And yeah, so this is the way you should generalize the factorization if this condition is violated, which has linear independent columns, okay? So if you want to move for a matrix that doesn't have linear independent columns, then what you do is that you sort of append whatever is no linear independent at the bottom, right? And then you just multiply it by the all zero block. Okay, very good. So the application of the QR factorization would be to solve linear equation and then least square problems. Okay, so least square problems is where we want to get because we said that least square it's one of the core mechanisms in machine learning, right? And this can be done very, very efficiently, but we didn't know before this call. We're going to see this, and then we're going to go from this to SVD, and then we also gain some useful formulas, because if we want to compute the pseudo inverse, then we can also use the QR decomposition for the pseudo inverse, and also for projections, right? So we saw that the projection operation is also something interesting for us. Let's say we want to project the data on some lower dimensional space, then we can do this. Good. So now let's go back and look at the QR factorization for the pseudo inverse, right? So if you have a pseudo inverse of a matrix A, right, we said that this is called A dagger, which is A transpose times A all to the minus 1 multiplied by A transpose. So in a sense, this is the one that we still don't know how to do it. Of course, the A transpose has no complexity for us, but sort of we want to know how difficult it is to express this pseudo inverse once we account for the QR decomposition trick that we just learned. So we just say that A is equal to Q times R, and we remember that Q is orthonormal. So Q times Q transpose is equal to I, and R is upper triangle. So R transpose is lower diagonal. So R times R transpose is it's a purely diagonal matrix. Okay, so you have we just follow the formula, right? So here we have a transpose, so we can flip them around here, and we have Q times Q transpose. So here it becomes R transpose times R to the minus 1. Outside we have R transpose and Q transpose. So just flip it around. Then here we have a minus 1, right? So we can bring the minus 1 in and flip the order, because this is invertible for sure. So this becomes R to the minus 1, R transpose times RT times QT. Now we have this beautiful thing that we have fixed. We have fixed that the elements on the diagonal are positive, right? So this R minus 1 and transpose. And R transpose actually gives you an identity matrix because R is non-singular. R to the minus T. You see why this confuses me, right? Because this is R transpose to the minus 1, and we write it R to the minus transpose. Anyway, you understand this. We take the transposes and we take the inverse. So when we multiply by the transpose, this gives you an identity. And so this beautiful object becomes R to the minus 1 Q transpose, which is very much desirable, right? Because if we had taken, it's very intuitive, right? Because we have multiple. If this is a pseudo inverse, right? So if you take the inverse of Q times R, of course this becomes R inverse times Q inverse, and Q inverse is Q transpose. So this is really what the result that we would have expected, right? So if somebody has told us that there is a pseudo inverse, and they told us this is the QR decomposition of the matrix, then we would have wanted the pseudo inverse to be R to the minus 1 Q transpose. And so it turns out that the definition of the pseudo inverse when applying the QR decomposition gives us what we wanted, what we would have expected from the first place. Okay, and then so if A is a square non-singular, then we go back to what we were saying before, that A to the minus 1 is equal to R to the minus 1 Q transpose. Okay, so if the matrix is invertible, then the inverse is exactly R to the minus 1 Q transpose. So let's go back and let's revisit the range definition, because now Q is very nice to us because Q is an orthonormal matrix. So if we know that in a sense it's a matrix of orthogonal vectors, and we want to see if this matrix of orthogonal vectors is helping us in the definition of the range and the span. So remember that the range of A is all the space that we can cover with the product A times X. So if A is linear independent columns, then Q times R factors are Q comma R, and Q has the same range of A. Then and we see this because if Y is range A, then we can take A times X. Instead of A, we write Q times R times X. But R times X, it's just reshuffling the linear combination, right? Because this is a triangular matrix. And so this is equal to Q times Z for some Z. And so this is the range. This is, we have the range of A is equal to range of Q. So in a sense, Q is the set of orthogonal vectors that we can build out of A. And so the range of A is actually just the range of this linear combination of vector, this orthonormal vector that we find inside Q. So in a sense, you can think that Q is really the matrix that contains all the orthogonal dimensions, and then R just shuffle them around with in some nice way, right? In some Gaussian elimination like way. Okay. So the columns of Q are actually the orthonormal basis of the range of A. So if we take the range of A and we impose, let's say, an orthogonal basis over A, we will have that the orthogonal basis over A will correspond to the one in the range of Q. Very good. Now the projection, which we saw before. So we have a point, and we want to find, we have a direction of the plane, and we want to find what is the length, right, of the vector that goes along the direction of the plane from the point to the plane. So A is equal to Q times R. So A dagger is equal to R to the minus 1 times Q. This tells you that A times A dagger is equal to Q times Q transpose. Okay. And so we saw it before, right? That this formula was used there. So this is X. This is the projection of X over the plane A. And this is equal to A times A dagger times X. And this becomes Q times Q transpose times X. And this is because the range of A is equal to the range of Q. Okay, so instead of having the hyperplane A, which is generated by all the linear combinations of the vectors, of the columns over X, then we have just the range of Q. Very neat, very neat. So it means that when we want to do the reflection, now we have a very nice way of doing the reflection just with the orthogonal direction of A. So if A is equal to SC times M, so if you go to complex matrices, everything again works the same. We just have a Hermitian definition of the orthogonal matrix. And in the diagonal of R, we have non-zero real element. Okay, so the diagonal contains real element. Remember that before we could impose them to be positive, but now they are real. And now, like a little bit of discussion on the complexity, right? So the Gram-Schmidt algorithm is 2m times n squared plot, and then so the Gram-Schmidt algorithm is how you obtain the QR factorization. Okay, then we're going to see this later, right? So there is the householder algorithm, which has a much lower flops, and then yeah, we're going to see this. We're going to see this next. Okay, so but basically, we have this historical algorithm for constructing the QR factorization that are very useful for us, and the one that we want to look at are the Gram-Schmidt one and the householder one. Let me check the time, guys. I don't want to go over like last time. Then you guys called me. Okay, we are over. So next time we see the Gram-Schmidt algorithm. Okay, it's gonna be very nice to us. Okay, we stop here. We stop the recording. So if you have any question, you can ask me the question. Stop. Go back to the YouTube people. Okay, guys. Sorry, I stopped in time this time. Sorry. Because we don't do the full class, so I don't want to go. Yeah, I don't want to end too early since we don't do the Friday class. Any questions? Again, apologies for posting the wrong link. Next time, just bombard me or send me a personal email or do something. Again, if I don't respond by the day, it means that I missed the meeting. And if you send a message in the weekend, my brain is already fried. Okay, any questions? Otherwise, I'll see you guys tomorrow. The challenge is it's kind of long. So if you need more time, just show me something next time, and then you can finish in 2 weeks, okay? Since I made a mistake, I don't want you guys to be stressing out, or I don't want you guys to go in autopilot and just use ChatGPT for the challenge and learn nothing, right? So please, yeah.